Good afternoon, everyone. Today, I would like to talk about constraining black carbon aerosol over Asia using the GEOS-Chem adjoint and the assessment of the long-term trend of OMI Aerosol Absorption Optical Depth, AAOD. First of all, I would like to acknowledge all the co-authors, David, George, Greg, Nicola, Zhang, Zifeng, Junji, and Yuhao, and the support from EPA START grant. It's well known that black carbon is the production of incomplete combustion of carbonaceous fuels, such as fossil fuel, biomass burning, and biofuel. And it's well known that the change of black carbon concentration play an important role in impact on the public health. On the other hand, black carbon also play an important role in warming the atmosphere. About 10 years ago, the warming effect of black carbon is kind of like 1/3 as much as CO2. And recently, a paper published by Tammy Brown showed that the black carbon warming effect is about 2/3 of the CO2. But now we are still facing some challenges in both the black carbon simulation and the uncertainty of black carbon anthropogenic emissions. And here in our study, we would like try to use the satellite measurement OMI AAOD to constrain the black carbon emission and to improve our understanding of the black carbon distribution and its climate effect. So here, I would like to show 4 different black carbon anthropogenic emission inventory. They are based on different years, where we can find that there are significant increase of the anthropogenic black carbon emissions in the last decade. And with the CCARS emission inventory, there are more hotspots over the mega cities. And here, the index B and the MAG emission show much larger black carbon emission over Eastern China. And our following results will be based on the CCARS emission inventory and replaced by MAG over China. Here, I would like to show the model performance with the above 4 different emission inventory in simulating black carbon. And this 4 site is the 4 sites that with the star over Eastern China. And except this site is the rural site, the other 3 sites are the urban site. And the black line is the observation, where we can see that the black carbon are underestimated in this urban site with all these 4 emission inventory. Well, in the rural site, with the make and index B emission inventory, which include the monthly variation, it can capture this monthly variation very well. Okay, before using the AAOD to constraining black carbon emission here, I would like to show the difference between the model and the observed OMI AAOD over Asia, where we can see that in April, the model is underestimated. And in this underestimated area, we have more the observed pixels in this area. Well, in October, the model is overestimated than observation, but like this area, we have less observation pixels there. And this number would also impact on our constraining result. And here, let's look at the black carbon anthropogenic emission before and after optimization, where we can see from the difference between posterior and prior, we can see an overwhelming enhancement of black carbon emission over broader areas, and up to a factor of 5. While in October, there are slight reduction over India and South China, about like 1 to 5%. Well, over northeastern China is about 10 to 50% increase. And what about the surface concentration? Here shows the prior and the posterior surface black carbon concentration over Asia and overlaid by the ground-based measurement of 20 sites with this color circle. And where we can see after optimization, the black carbon surface concentration are improved, especially in the spatial gradient. But there are still some sites that the adjustment is not enough, such as the coastal sites and the sites over the Western China, where the prior emissions are relatively lower. And from the scattering comparisons, we can see this low bias has been significantly improved. And the linear regression slope values between model and observation increased almost a factor of 4. And in this study, we also discussed the impact of different prior emissions. We also discussed the uncertainty of this optimization, such as the different prior emissions, the observation operators, and the different inversion approaches and the resolution errors. Here I would like to mention that compared to the cost model simulation and the result of Punger, which indicate that the resolution error may be up to a factor of 2 to 2 points when compared with those ground-based measurement. Now, the above result is based on the short-term period, like 1 month. And we know that the long-term trend of the black carbon is also very important to understand climate change. But before constraining this long-term trend, we should have some basic idea of how about the long-term trend of AAOD. And in the past century, the global atmosphere burdens of black carbon has increased, especially over Asia with the rapid economic and industrial development. The anthropogenic black carbon emission increased significantly. However, in United States, with the emission control policy, the anthropogenic emission have been declined about like 50% in California from 1998 to 2008. So it's kind of like in the source region, the black carbon emission increased. However, in the local area of the United States, it's decreased. So, and how about this long-term trend of AAOD over United States, and what is the major factor that's controlling this long-term trend? And this figure shows the OMI AAOD trend from 2005 to 2013, where we can see a significant increase over like Western United States, Central United States, and Eastern United States, everywhere, almost. And the maximum increase is about like 10 to 15% in these 9 years. And AAOD increased. How about AOD? This is the AOD trend. Very different. It's similar to Randall's work that where shows the NO2 shows also show a decreasing trend over United States. Here the AOD is similar. But we did see a little bit increase in Central United States, and we found this may associate with the decrease in precipitation, where also show a slight decrease of precipitation over the Central United States. And then we defined 4 areas like Western US, Central US, and Eastern US. And now let's look at more details that's compared to the fire, the black carbon biomass burning in the last 9 years. So now we can see the AAOD increased significantly in these 3 areas. However, the black carbon biomass burning is almost like flat. It didn't change too much, not significant increasing trend or something. And we also take a look at the ground-based measurement of black carbon, the improved data, to see, well, with the emission control and the decrease in diesel black carbon emission, wherever in Western US like California and Arizona, it shows significant decrease of surface black carbon concentration. And also in Central US, this is Texas and Kansas. They also showed a decreasing trend of the surface black carbon concentration. So, and how about the seasonality of this trend? And then we also look at different seasons. We find it's almost in all the seasons that showed increasing trend of AAOD. The maximum was showed in summer, Central US and Western US, and fall, Central US, and spring, it shifts to a little bit to south. So let's look at the time series of a different season with the biomass burning emission of black carbon in the AAOD. We see that in Western US, in the summer and fall season, that this increase in the last several years is associated with the black carbon biomass burning emission. But we don't know in winter and spring what is the major contributor because there are not very close correlation between biomass burning and the AAOD. And this is central US. And in central US, only in summer, that's the interannual variability of biomass burning emission are consistent with that of the AAOD, interannual variability. But other season, we still don't know. Here in eastern US, and in eastern US, the AAOD increased since 2010, and in all of these 4 seasons. But we still don't know what is the major factor that's contribute to this increasing trend. Okay, from the above analysis that we can see a significant increasing trend in over United States, and it's related to several factors. Weather position, but we only see in AAOD. We didn't see that in AOD. It means it may not dominant by precipitation except part in central US. And emissions, but we know that emissions for anthropogenic emission, actually it's decreased, but and it's only associated with part of the biomass burning emission in fall and summer over Western US. How about transport? Is it due to the transport from Asia that's increased recently? We still don't know. And the composition change, it's kind of like that they have more absorption aerosol in the atmosphere because only the AAOD increased, but the AOD decreased. It means only the absorption increased. We still don't know. That will be our next step to check more details or some of the other factors. And the other thing is it a decadal trend or it's only happened in the last few years? Yeah, welcome to have any comments and suggestions about this major factor that's contribute to the increasing trend of AAOD. Thank you, that's all.
All right, are there questions for Liu Zhang? Yes, Orlando.
You know, the first part of this study about the white carbon emission burden, I would expect the AOD would be, AAOD would be affected by, probably dust, by weight to be able to. Why only black carbon is a control variable?
Why only black carbon more?
As black carbon emission as your control variable.
Actually, in our study, we already consider. Oh, we can use this. Okay, thank you. Actually, in our constraining, we already include dust. In our model, we also have dust, and this is the total AAOD. So it's already include dust.
Right, but when you invert the emission, you only invert in the BC.
Here, I only show BC.